Irfan, go.
Okay, hi. So yeah, welcome everyone. We are very pleased to have Matt Insall here for our this month's Relatorium seminar. Before I introduce Matt and his topic, maybe I should also announce that if you like our videos, I believe we have plans to create a website containing a repository of them soon, and we also have an in-person session at the AMS sectional meeting in Hartford, Connecticut in April, where we'll have some more talks that will also go on our website eventually. So today's talk is actually very special to me because it relates to non-standard analysis, which I also work on, and Matt has been working on for more than 25, 30 years at this point. So Matt has a very unique background of having a dual degree in chemical engineering and mathematics, and then he switched companies and has been doing it since then, and recently retired from Missouri University of Science and Technology. He will talk to us about non-standard methods and universal algebra. So, Matt, I'll leave the floor to you.
Thank you, Irfan. It's good to be back in the Relatorium seminar this month, and I appreciate being invited to speak. I will do a different kind of talk than a lot of people do in various places, but also very different than I normally have done. This is more like how I taught foundations of mathematics when we did some of it online. But I welcome questions throughout, and that's part of the reason that it will be different, in the sense that I may even ask you questions and hope that you respond. The whiteboard that I've got here is hopefully available to everyone. If it isn't, I'll have to figure that out. But it looks like 15 people have access at the moment. So if that's correct, you can add your thoughts as you ask questions and as I ask and answer questions. So today we're talking about non-standard methods and universal algebra. And I've got some things here for you to glance at while I blab for a bit. The abstract itself is on the left. And so if you had a chance to read the abstract, then you're familiar with that already. And the underlined things are things I'm feel like I need to introduce and discuss so that we can have a foundation for our conversation today. Quickly, on the right, I've got some notation, and I'm sorry, I shrunk it a little bit, but it went too far. On the right, I've got notation, and then when I scroll down, there's some more notation, and then we'll go to a blank whiteboard where we'll just, part of the goal will be to fill it up with stuff. Okay, so on the left, we're talking about algebras can be thought of as a universe of discourse for a computer that runs deterministic code. And by deterministic, we mean you get some inputs, but you only have one output. And so these are functions in the mathematical sense. So every algebra has an underlying set, A. Blackboard bold A is the machine built on A. The unblackboard bold A is the underlying set. Those are the things the machine works with. The ends of A, that's the family of nullary operations. We sometimes call them constants. They take no arguments. So An element of n sub a is a function f sub I a. The decoration at the top just tells me which computer I'm talking about, or which machine, or in the Universal Algebra parlance, which algebra I'm talking about. And f sub I a is the implementation of the ith operation f sub I in that machine A. And this goes from A to the 0 into A. And that means it just takes no arguments, but outputs an element of A. This kind of function here, a unary operation, is what we're usually referred to as a function. So it goes from A to the first power into A. That's why it's called unary. And there's a family of them, by the way. The set I sub n is a set of indices telling me which operations have no arguments. The I sub u is the set of indices for which those operations take only one argument. I sub b is the collection of indices for the operations that take two arguments. And sometimes in physics, these are called pairings. You take two arguments, you get one output. And then there are possible ternary operations, quaternary operations, and so forth. So the arity can be as high as you like. We will stick to finite arity, and so that makes life a little easier. I have a PhD student working on infinitary operations as well. I want to move down real quick, where I've already got something else prepared for you. All right, so on the left here, we still have the abstract, and the next underlined thing is an important part of this, the notion of a formal language. I don't know how I got that weird arrow there. It's got to go if I can accomplish that, but I don't know how, so I'll just have to wing it here. That weird arrow right there, it somehow jumped up there, and I don't know where it came from. Okay, so reviewing a little bit, the set I is my index set, and it's partitioned into subsets based on the arity of the operation. Arity of an operation is the number of arguments it takes. F sub S, S running through I is the collection of all operation symbols. That's what they're called. With no decoration at the top, the no blackboard bold A, that's an unimplemented operation. It's just got a rule saying how many arguments it takes. That's all. It's just a name. Like plus is the name of addition in everyday arithmetic, but if you go from one calculator to another, you might get a different implementation. For example, adding matrices is different from adding numbers in the sense that a matrix is a different kind of object. Adding complex numbers is a little different than adding real numbers in the sense that the arguments can be complex numbers, but that's one of those kinds of distinctions that most people don't have because they like to overload operators. But adding times on a clock is significantly different from adding places, let's see, vectors in the complex plane or numbers on the real line, for example. So the addition on a clock would have to have a different decoration. It'd still be a plus sign, but you'd have to put something up there to tell you which clock you're looking at, whether it's a 12-hour clock, 24-hour clock, or you're dealing with a place on some planet operating a different, let's see, orbiting a different star that has 7 hours in a day instead of 24. Okay, and then our formal language has a lot of variables, and you use them very much like in logic, in other logic systems, and equality symbol has to be there. And they're always universally quantified. So upside down A, V is called a V quantifier, and a formula is always of this form. It's a universally quantified equation. There are no ands, there are no ors, there are no implications, there are no existential statements allowed in this language. But an abbreviated formula, since all the quantifiers have to be universal, an abbreviated formula is written just as an equation where this tau 1 and so forth can be expressions that involve various operation symbols of various arities depending on what you're wanting to do. And then on the right, the sigma 1 also can be an expression involving the operation symbols and variables. All right, one more, and then we move to, well, we've now covered
We have a
just
question, Matt.
introductory language for universal algebra. Okay, Irfan?
We have a question that says, where do V1 and V2 appear in the equation?
Oh, so that's a very good question. Thank you. So the tau 1 here, that can be F sub 37 of V1, V2, F sub 22 of V3, V7, etc. Okay, so, and tau 2 can be some expression like that as well. So the variables occur in arguments of some of the functions, or further down in the term tree is what it's called. Okay, I don't want to go into details about the term tree. A lot of computer scientists already know that. So now to nonstandard methods, which is the part that's going to be new to most people who have already seen the computer science and universal algebra type stuff. So, and maybe everything is new to you. So in that case, I rejoice in being able to introduce you to this subject. So in nonstandard methods, we have a universe, like it's a playground of mathematicians. It's based on set theory. And you have a first order predicate language rather than the language I just described, which is a fragment of a first order predicate language. And here, in this universe, we have a set A. Let me change the color so that I can, so we have this set A. In there may be finitely many things. Oh, it's not just a set, sorry. It's an algebra. So it's a set with all that extra machinery to do computations. And then containing the underlying set, that's what the A was, the undecorated A was. Containing it in the large here is star A. Now that star A, you can think of it as being the way that some other observer views A. They see more things in some sense, but there are some things that they don't see. And we'll talk about that later, what they don't see. But the main thing is they don't see that this set H that contains the original A is not finite unless A is finite. So the H here is what I call a hyperfinite set, or we call it that in nonstandard analysis. And all such H's obey the same kind of rules as finite sets in the what's called the standard universe. So the standard universe is basically this part. And things outside that are sort of non-standard part of the universe. And we as mathematicians and scientists get to see the whole thing, both universes, the standard and the non-standard. So we're sort of having a discussion about what someone can see. A standard person and a non-standard person. And the non-standard person is limited in what they can see. The standard person can't see the stuff outside of the standard universe. Yes.
Matt, sorry, I meant to ask a question before we move too far, but you said that star A can't see certain things about A, which seems, I mean, and that's fine as far as it goes, but it seems a little contradictory to the fact that it's bigger.
Yes.
Visually, it seems to imply that it sees more things than just A.
So, for example, when we say that what it sees and what it doesn't, what it sees is called internal. And what it doesn't is called external. Thank you for asking the question. An example of an external thing from the viewpoint of star A is A itself. Unless A is finite, in which case star A and A are the same, and they see the same things. Okay. An internal thing that star A sees is any finite subset of A. But the infinite subsets of A, star A can't see. It can't tell where they end and where things that are not in them start, essentially. So let me give you a way to see the natural numbers this way. I'm very glad you asked the question because this is something I need to put in here. So if A contains the natural numbers, then star A will see not the natural numbers. Well, I shouldn't put that, but the non-standard natural numbers. Okay. So what's a natural number? A natural number is a number that we use for counting. We start with 0, we count something that has 1 element, something that has 2 elements, and so forth. And all the natural numbers are contained in this first part of the tape. And the things that are outside that part of the tape, they're in the non-standard world that star A gets to see, but A doesn't. And I'm using the letter nu here for what we call an infinite non-standard natural number. It's called infinite because it's in that part of the tape that's beyond all the natural numbers. So everything down here is less than everything up there. And the star A and star N cannot tell where this divide is. They don't get to see it.
And Matt, yeah, is it right that in this picture to interpret your earlier statement as saying that from star N's perspective, all these
exactly
infinite cardinals nu are finite? It doesn't see them.
Yes, yes. The star N thinks they are finite. Star A thinks they are finite. All the things that are starred think that nu is finite. And we as mathematicians and scientists outside, as normal people, we know better. We've built the universe so that that information is hidden from the non-standard observer. And from the standard observer, this part of the universe is hidden altogether.
So just to further clarify, given any nu, someone living in the non-standard universe would still see all the non-standard natural numbers up to nu, which of course include the set of natural numbers.
That is correct. It
But
sees
they
all
would
of
not
them,
see, yeah.
but it can't see where they stop, where the standard ones stop and where the non-standard ones the infinite ones begin.
Yes.
Because it doesn't call anything in there infinite.
Yeah, from their perspective, everything is standard. Even the new is standard for
Yes,
someone living in that
yes.
universe.
That's right. You could do, and this is related to your research, you could do this again and you could have a double star n that can't see the divide between star n and the things that are non-standard with respect to it. That's a little more advanced. Okay. Now here's the thing. One of the very important things to study in universal algebra is when is an algebra A? When does it have this kind of property where all the finite algebras in it have a certain property? For example, suppose you have a group. So for the mathematicians in the audience, if you have a group G that's infinite, but all the finite subgroups of it are what property do I want? Let's say abelian, one of the simple properties. So they're all commutative. Then this H, this group H, that contains the original group A, would have the property, and by the way, this H here is the subgroup generated by this hyperfinite set. This group H would be abelian as well. And that's because of something called the transfer principle. And I'll call it transfer up. Properties of A, and I'll say A, but it's any the properties of the standard universe can be viewed as true of star A. So for example, if A is commutative, star A is commutative. But you have to be careful about what kinds of properties to some extent. They have to be when you express them. So for example, if we go back to one of these equations up here, then if we replace the Fs with star Fs, and we keep everything else, we put stars on all the operations, and we put an A up, a star A up here, and the equation star F. Let's see, my pen's not always working for some reason. Star A. If we put stars on all of those operations in there, then and decorate them with star A's, then if that equation was true when you erase all the stars, then it would have to be true here as well. And that's because it's a first order property. So I said properties a moment ago, but I should say first order. Okay.
Matt?
Yes.
I wonder if then what you're describing, just for context, is essentially properties that you want this star functor to have. Essentially, you're trying to describe star operation in a functorial way. In other words, how it commutes with which sentences,
very good,
the underlying algebras it commutes, and so because you haven't told us what star does, you just said it's an exterior perspective of this algebra, and
exactly
right
now.
Okay,
Star is, that's a very good, the star operation is an embedding. So I don't know what I'm doing wrong, but every once in a while my pen just decides to not work. I apologize for that. And the sense in which it's an embedding is it preserves membership in set theory. And since it preserves membership, it preserves containment. And since it preserves all those things, it preserves all the other mathematical properties we express using membership and containment. And one of those ways is the semantics as it's built up in equational logic, which is what I described up here. Equational. Okay, what in the world? Equational logic is a fragment of first order predicate logic that only uses universally quantified equations. Okay. And so the star has two meanings here. It's a syntactic transform. So it's overloaded, by the way, as I mentioned earlier. It's a syntactic transform. And what that means is that star can be applied to elements of the language like operation symbols and not variables, only the operation symbols and universal quantifiers. But we neglect the universal quantifiers because they're assumed to be there all the time. And it also has in its overloaded domain the elements of my universal set theory. So it preserves this structure semantically, and it preserves the logical system syntactically, and it's an embedding in both senses. Okay, and it's an embedding, not an isomorphism. But whenever we restrict it to finite structures, if we look at it restricted to a finite structure, it's the identity. Okay. I say finite structures. Finite structures, we have to be, there's a little bit of a caveat. If the finite structure is complicated and built up from your structure A that you started with, then it's not the identity, but it's an isomorphism. Okay, for those parts.
Matt, one more question.
Yes, more questions.
Maybe I'm getting ahead of myself, but I know since I do non-standard analysis that you can embed A inside a hyperfinite set. But you mentioned that you are embedding it inside a hyperfinite algebra. Is that right?
Right. Okay. That's very good. Thank you. So A is contained in H because I've decided to treat A as being contained in star A, and I've chosen to consider the fact that A can be expressed as a union of all of its finite subsets. So if I look at all the finite subsets down inside here, okay, what's going on? Then they union up to give me A, okay? And there's a principle that I didn't mention yet that's useful here. We've got the transfer up principle, and then we have the concurrency principle. And this is related or equivalent to overspill. And in this context, what that gives us is that if we consider the finite subsets of A, then as long as star A isn't equal to A, we're guaranteed there exists a finite subset, a member of the collection of sets that star A thinks are finite that contains all of the finite subsets of A. And that's the overspill principle, or it's also the concurrency principle. And what it's a version of it. And what that gives us is that when we draw H, we have a hyperfinite subset of star A that contains A. But as you might remember, if you've done any algebra, sometimes you can have a subset that's not closed. So the H here is the smallest internal. Remember I said internal. So an example of an internal thing is, well, H is internal as a hyperfinite subset. Let me fix that. I should have put a comma, H. But then this blackboard bold H is an internal subalgebra of star A. And it's internally generated by H, meaning that it's the smallest subalgebra of star A containing that hyperfinite set that contains A.
But
now,
the ground set
that
of
only
the
works if A is, oh, no, H is hyperfinitely generated. So this is hyperfinitely generated. This is hyperfinite. And here's one of the earliest theorems. The only way that this algebra A can be locally finite, meaning that every finitely generated subalgebra of it is finite, is if there exists one or more hyperfinite algebras containing A. Okay? And that would mean that here's how you do that. So the transfer principle up says that if H is hyperfinite contained in star A, then it generates a hyperfinite subalgebra of star A. But we've got H containing A, so this hyperfinitely generated algebra has to be a hyperfinitely, not just hyperfinitely generated, it's an extension of A in the sense that A is a subalgebra of it. Okay. If you think of groups, A is a subgroup of H, and H is a subgroup of star A, but H is hyperfinite, so star A thinks it's finite.
So to summarize, in general, H is only hyperfinitely generated, but when you impose the condition that your original algebra was what you call locally finite, then
Yes.
A theorem says that H actually ends up being finite.
That's
sorry,
one
hyperfinite.
Yeah, that's one direction. The other direction is that if you could find a hyperfinite extension of A, then A had to be locally finite to begin with.
Okay. We have
So
a
it's a
question, I think.
Yeah. Sorry. I a thing that I thought might need further clarification, although what you were just talking about also, well, I would love to hear a little bit more about the distinction, the importance of local finiteness to make it finitely generated and guarantee hyperfiniteness, in other words. But the earlier question was, when you're extending, you're coming up with this H, even the set H that contains the original algebra, clearly, as Irfan's question initially implied, we're not talking only about extending a set, but also extending all the operations and so on. So, as you pointed out in the, where is it up here? The operations themselves are starred, right?
Yes.
So do we need to talk about how that's done? It's not just adding new elements, but defining the operations on those new elements.
That's a good question. The transfer up principle doesn't tell you how they're defined explicitly. What it says is they have the same properties as the originals.
Right. So there's no uniqueness implied or whatever. You're just considering all the ways in which that might be possible. It's a constraint.
Yeah. Now, the thing is, you can prove separately that once you make the extension and you decide how star works, and there is a way to do that. It uses ultra filters, and which is outside the scope of the talk. But once you do that, then it is unique. You have no choices. Yeah.
Understood. But at this point, I am justified in thinking that it's underspecified. It might not be unique, right?
Right, and the one of the reasons is that there's proper class many ways to do the star. So there's all kinds of ways to do it. Yeah, but all of them have this transfer up property, which might be called a reflection principle or something like that, that the properties of star A reflect the properties of A and vice versa. The transfer down is the vice versa part.
Right. And then just a slight more clarification, if you don't mind. I don't want to go too far on a tangent, and maybe, you know, it'll become obvious with examples or whatever. But regarding this distinction that Irfan also articulated, the necessity for local finiteness, the local finiteness assumption, which then guarantees that that the algebra H that's generated is a hyperfinite subalgebra of star A. Like the distinction between finitely generated and locally finite, for, let's say, for us not experts, and from which perspective are we looking at it? Is it from the star perspective, you know, the finiteness aspect of it, or is it hyperfiniteness?
Oh, in A, it's local finite. So in A, local finiteness means just what I said, that every finitely generated subalgebra is finite. So an example of that, which might help illustrate it, is if we take all of the groups Zn for natural numbers n, and now we take, those are finite groups, and we take the direct sum of them in the usual sense that mathematicians use, then that's locally finite. And it's locally finite in some sense because it's built up in a nice way from finite structures.
Essentially because all but finitely many of them are zero for a generic element.
Yeah, if you take any, so here's a nice way to see it that is related to a theorem I had in my dissertation. If you look at the direct product of those guys, then the elements here are vectors of the form x1, x2, etc., where the x1 is in z0, not z0, but anyway, I should have taken out 0 and 1 here, okay? So z2, x1 is in z2, x2 is in z3, etc. And there's only 2 elements in z2, and only 3 elements in z3, and so forth. But if this has infinitely many non-zero entries, then it can be a member here, but it's not a member here. Okay? And only things with finitely many entries exist in this group. Okay? And if you add any 2 things, you use addition for your operation here. You add any 2 things, you add them like vectors. And so you cannot get any non-zero entries in place of 0 entries when you add finitely many things. And because of that, this guy's locally finite. It's a bit of an argument, but it's not too hard. Okay? And yet this is not locally finite. Okay? Because you can...
Sorry. And on top of this, now the finitely generated extension of something like this, let's say the star or the,
yes,
you know, that you were talking about for the H algebra, what would that look like?
H has this guy as a subgroup and this guy as a supergroup, a group containing it. No, it doesn't. I'm sorry. It has this guy. Containing it. Okay. Now, what's this guy here? I'm going to put a star here. The n goes over star n. Okay, wake up. My iPad stopped responding for some reason. Okay, there we go. Take out 0, 1. Okay. So if you remember the tape, then this one's built on this part of the tape. This whole thing is built on the whole tape. And this guy is built only up to some new. Okay. Well, of course, that one contains that one. And of course, this one contains that. Sorry. Of course, the containments work the way I've got them written. Okay. And because the vectors in H are of length nu for some infinite nu.
Right. And then the aspect of it being finitely generated from the star perspective, how do I know that? What does that entail?
You can find a hyperfinite subset of this guy, of the first one. Sorry, a hyperfinite subset of the non-standard extension that contains all of this, but it might not be closed under vector addition. And by vector addition, I mean the usual addition like vectors, but over modular arithmetic. And the modulus can be infinite.
All right. So that
infinite hyperfinite.
So basically any subalgebra then of the star version, any star algebra of the star version would be finitely generated from its perspective.
Right.
Or finitely generated, right?
Because if you take a vector, if you take a hyperfinite collection of vectors in here, then there's a longest one, right? And outside there, you only have 0 entries. And you can't change them to non-zero entries by addition. Okay.
Even hyperfinite addition, because
yes,
right,
yes.
That's the difference.
Right. Now you could break this. You could break all of this by supplementing the operations on the original group with a successor operation. Sorry, with a shift operation. Okay. So if you define a new operation that takes a vector x1 and so forth to 0x1 and so forth, then the argument doesn't work quite the same, if it does work at all. And here's why. Here's why, because
this is,
pardon?
It seems to me then this is another non-trivial constraint on this star construction, that, in other words, the ability to do that entails a certain extra choice that you are making that's not implied.
It all has to do with what operation, what algebra you're going to start studying at the beginning. So if I supplement my group in the first place with another operation, so if my underlying set is the direct sum that I talked about, so the infinite vectors with almost all 0 entries. And then my operations are the usual ones, addition, and I'm talking about a group, so I need a 0 vector. And then I need a unary operation, which is subtract, additive inversion, okay? And then I need my addition operation, my binary operation. So that's what I started with in this discussion. And then if I expand my language to include another operation, which is this shift operation, and I interpret it in this this structure as a shift, like I did up above, then that is no longer a group because I've got this extra operation, but it also has this property that if I want to find a closed subset of star if I want to find a closed subset of the enlarged structure, then it to be closed, if I have any vector in it, I also have to have the vector that I get by shifting it. Okay, and that's going to increase the lengths of the vectors in the set. So closing a set always gets a set with arbitrarily long lists of non-zero entries. And because of that, it's not going to be locally hyperfinite here, and therefore not locally finite there. But if it's the direct sum of these abelian groups, it will be locally finite.
Matt, just a reminder, we started a bit late, but I think it's been about 40 minutes, so maybe
Yes.
we should head towards some theorem or some
Questions.
conclusion, and we can have questions or discussions after that.
So I'm going to ask a question. I would
Okay.
like to know from the audience if they have a favorite kind of algebra and property of algebras that they would like to investigate just very briefly here in this context. I talk about groups here a little bit, but there are lattices, rings. These are all some of the classical kinds of structures that you can study this way. And we can study other things besides local finiteness this way. There's been some things in the chat, but they're probably goodbyes. Oh, Dwight Williams did point out group example, infinite non-abelian group with proper subgroups, all abelian. So that's not a question, but a good example. And pointed it out, mentioned it as the Tarski monster group.
Yeah. Here's an example that I'd love to maybe ponder about, like the ring of polynomials.
Okay. Okay. So if you take
over the integers, let's say, or something.
Over the integers. So that's z square brackets. I got to wake up my iPad again. Let's see, can I? Z square brackets x, where x is your indeterminate or your variable. Okay. So if we look at its non-standard extension, a typical element here is going to be, we'll call it P of X as usual. It's a sum, J. Okay. It must be a broadband issue here. Sum from, say, J equals 0 to N of AJ X to the Jth power. So the elements are expressions of that kind. And then here, a corresponding, so a given polynomial like that would get mapped to star P which is, it's got the same formula, J equals 0 to N AJ X to the J. So that's this embedding that I'm talking about. It's the identity on this. And so that's contained in there. Okay. But then in this extension, there are others like Q of X
Well,
equals the
right.
sum.
In particular, Matt, I think there are two distinctly different others. Ones where the coefficients are hyperfinite, and ones where the coefficients might be finite, but there are hyperfinitely many of them. Is that correct?
Yes, that's correct. So these get mapped to these, and then the generic kind of member over here is of that kind where the RJs don't just come from Z, but they can come from star Z. And that's what you're talking about. You can have.
And the fact that nu doesn't come from n, but from star
That's
n.
right, exactly. Nu can be infinite in the parlance of non-standard analysis. We call things that are on the extreme part of that tape infinite.
So
Infinite
I wonder,
natural numbers. Yeah.
I wonder, would the transfer principle allow you to carry over the factorizations, the
Yes.
fundamental theorem, things like that?
Yes, it
And
does.
would you have to enlarge the set of primes to accommodate?
Yes, it does. Yeah, you already got a larger set of primes anyway, because if you look at the tape here for just the natural numbers, then so we have properties of certain numbers down here, we call them primes. Okay. And
I was
that
talking
means,
about prime polynomial, like irreducible
okay,
polynomial.
yeah, that's true too. Yeah. So prime and irreducible get carried over as well. Yeah. But one of the main reasons is that the formula to describe them mathematically refers only to the polynomials themselves, or well, refers only to polynomials in general, and those are finitely long formulas. They don't have infinitely many ands or ors or anything like that. So when you write down what it means, so I'm going to get rid of my tape down here because I misinterpreted your question. So if I have a Q like this, then a theorem that you know because of transfer is that there exists a way to write Q as a product from J equals 0 to, and I'm not going to use nu, I'm going to use mu because it might be not the same number of factors, especially if they're not all linear factors. Okay.
Right, and there's multiplicity questions,
That's
presumably.
right. That's right.
Yeah.
Let's call them f sub j of x, and the f sub j of x might be a product itself of irreducible polynomials. But one of the theorems is you can make sure that the fj's themselves are irreducible if you put appropriate powers on them here. And those, the alpha j's can be infinite, and the degree of your irreducibles can be infinite as well.
But then the sums of the alpha j's would be equal to nu in some hyperfinite sense?
The sums of the alpha j degree of fj,
Yes, yes, yes.
that sum is equal to nu. Yes.
Okay. And there's uniqueness to this among the monics anyway, like there would be for Finite?
Yes, yes. And that is correct. It is uniqueness among the monics. That's right. Exactly.
Wow. Okay. And presumably, I guess we could even my mind was going to, okay, what's a new prime that is not like a finite prime? And in the sense that, the ones that would be like the finite primes would be something like, x minus a hyperfinite constant, right? but are there other kinds of primes that are not like that are not extensions of, are all the primes extensions of finite primes, or are there other primes in this setting?
Let's see here. I'm trying to think of a kind of straight, very immediate kind of thing. Yes. So we know. Let's see.
What I have in mind is, you know, in the standard setting, and over the reals, which is what, well, over the integers, you have certain, you know, classes. There's quadratic primes, and there's irreducibles and linear irreducibles.
Yes.
Is there? I mean, essentially, if we can
Over
make
the
the case,
non-standard reals, you'll have that too.
yeah. So if we can make that case, which has been basically the thrust of your presentation, that essentially we can use
over the reals, it won't go higher than 2.
Right. Yes,
all the irreducibles over
exactly.
the reals are quadratic.
Yeah, exactly.
For the
all I'm saying
non-standard
is,
reals, that same thing will hold.
Right. So Matt, all I was getting at, I mean, this is just an example. It's an interesting example, I think, but nevertheless, it was just meant as an example to illustrate that essentially what you're describing is a strict enlargement, a process for enlarging the language with which we describe certain operations. It's not going to, but you're not looking for it to have new phenomena. You're just trying to see how far the existing phenomena can be enlarged, so that I'm almost like wrong in expecting to find something that wasn't there before. Is that correct?
It's called a conservative extension. So the part of the fact that the transfer principle expresses that the syntactic transform star and the semantic transform star are embeddings and have this extra property that the embedding is what we call elementary in logic, that it preserves truth both ways. Okay.
Exactly.
This is the conservative extension of the standard world.
Exactly. Yeah. So it preserves truth. So it's, I mean, to me, then it feels like it's sort of like part of model theory, right? I mean, it's basically just modeling a set of requirements of you're instantiating a universe, as you were saying, with maybe a different language. But it's the same. Both universes, both representations entail the same truths, both ways.
Yeah, the thing though is that if you want to prove a theorem in the standard world, let's call the theorem T for simplicity here, then if you're going to use the non-standard world to do it, when you look at star T, the transformed form of the theorem, if you can prove it in the non-standard world, then T is true in the standard world. Okay. But when you do the proof, you can use things that the standard world can't see. Okay. Now, the same thing holds the other way. If you have a proof in the standard world of T, then you can prove it in the non-standard world, prove star T in the non-standard world. There's an effective procedure for doing this both ways. Okay. Now that may sound like non-standard methods don't gain you anything because of it being a conservative extension. And if what you're really interested in is proving stuff over here in the standard world, then but the fact is there are theorems in logic by people like Kiesler and others that address this issue. There exist theorems in the standard world that are so complex that you won't be able to prove them in the standard world in less than the lifetime of the universe. I'm very roughly paraphrasing what their theorems say. It has to do with pi 0, 1 comprehension, pi 0, 0 comprehension, and so forth. And yet the comprehension there is lower, and so you're able to prove it in using non-standard methods in the lifetime of a human being. So
the exact reference is by Kiesler and Ward Henson from 1986.
yes.
It's a paper called The Strength of Non-Standard Analysis.
Yeah.
Actually,
Yeah,
that's a
thank you.
good
This is where
point
I thought,
to.
this is where I thought you were going. So thank you very much for clarifying this. You're making these two universes as close as possible so that they entail the same truths, but their inference engines are different, vastly different. And so in one case, you can make inferences, you know, much more rapidly than in the other case. Like, and obviously the traditional place where we all have seen non-standard methods, namely differentials and calculus, offer a great example, right? Or infinite probability theory, for example, or non-countable probability is another example. And those are the places where you can get to results much more directly without, you know, sort of eschewing all the delta epsilon stuff and all the sort of limiting questions. I'm sure, Irfan, you also have a lot to say about that.
Yeah, no, I was just going to say that it seems like a good point to steer that discussion towards an end, and not necessarily ending right now, but since we already started talking about comparing what we can do standardly and what we can do non-standardly, maybe you can give us a rough overview of the history of how these methods developed and how they have been used, and we can wrap up the discussion that way.
Okay. So in pre-1900s, calculus was developed using infinitesimals, and then and so you can go back to Archimedes and even a little earlier, and his method of exhaustion. It calculates areas by imagining dividing them up into infinitely many, infinitely small pieces and adding them up. But it actually is very much like limits as well. And so later on, people like Fermat, and some people don't realize that Fermat had a theorem in calculus. It's the most important engineering theorem, and it's proved using infinitesimals. And why is it the most important engineering theorem? It has to do with optimization. Fermat's theorem says that on any closed and bounded interval of the real numbers, a continuous function achieves its maximum and minimum only at the endpoints and critical points on the interior of the interval. So you use differentiation, and which is developed by Leibniz earlier using infinitesimals, and Newton independently, and they got in a big argument about who was first. But they both use infinitesimals, although Leibniz called them infinitesimal and differentials, and Newton called them fluxions. And roughly, a lot of mathematics and physics was done, and now some things that are called engineering. But then also, the philosophers were interested in where this took humanity in some sense. And Berkeley was a philosopher, and he pronounced he called this the works of infidels. I'm running out of battery on my iPad, so I won't be able to write anymore, but I can talk. So he called it the work of infidel mathematicians. then mathematicians like Cauchy and Lagrange and others developed, I think it was Lagrange, maybe I'm mistaken, but they developed a different approach using limits. So, oh, it's not big enough, I guess. And then that was in the 16th, 17th, and 18th centuries. The 19th century and 20th century brought on a lot of geometry and alternative ways of thinking about certain things. And one of the things that happened then was the Lobachevsky and Bolyai. That's not the way they're usually written. It's usually written Bolyai, Lobachevsky. They proved that Euclid's fifth postulate cannot be proved from the other axioms of geometry, Euclid's other axioms. And that wasn't known until then. And Riemann also found a solution of that problem. And the reason I bring that up is it showed that that you can have incomplete axiom systems. And in the 20th century, it was shown that number theory is one of these as well. Forms an incomplete axiom system, at least first order number theory. And if you try to go to second order number theory, the person that answered this, or the people that answered this question, include Turing with the halting problem and Gödel.
Matt, I think you have to scroll your whiteboard because I see you're writing something, but it's not appearing. Maybe scroll down a little bit.
Oh,
can people see it?
I'm just typing. I see it on my.
I think everyone can do it on their own. I have control of the whiteboard. Yeah, you can control.
And so Turing and Gödel proved the undecidability results. Turing's was called the halting problem and sort of started modern computer science, although Babbage built a computer in the 19th century and continued in the 20th. And Gödel proved that, I think I got the wrong symbol there. It should be an umlaut. Gödel proved the undecidability of number theory a different way. Turing's approach using dealt with what's called the Entscheidung problems. And Gödel proved that that if number theory is a consistent axiom system, then there exists a formula that says that number theory is consistent, and the number theoretic standard logic system. I'm sorry. Turned on do not disturb, but it didn't work. Gödel showed that first order number theory is an undecidable number system, an undecidable axiom system. And that means that there are he showed it in a very specific way. He showed that you can formulate in that system the statement that number theory is consistent. And then you can prove that number theory cannot prove that statement. That means that either it's inconsistent or it's incomplete. And incomplete means we need new axioms if you want a complete system. And inconsistent means it proves everything. So if it's complete, it's inconsistent. And if it proves everything, then we have no information we get out of number theory. And then in the teens and 20s, Abraham Robinson was born and grew up as a mathematician. And I'm skipping a lot. And he tried to solve a problem he solved a lot of problems in pure and applied mathematics, and he worked for a while for the Royal Air Force. But in 1970, he solved a problem posed by Hilbert, as I understand it, and probably others, asking that this concern of Berkeley be addressed to prove that there is a rigorous foundation for using infinitesimals in mathematics, and specifically in calculus and analysis. And he did so in 1961 or thereabouts, interestingly, the year of my birth. And he called it nonstandard analysis. Now, he was already familiar with nonstandard models, because one of the ways of approaching the incompleteness of number theory and the undecidability of number theory is to use nonstandard models, but also various mathematicians in the early part of the 20th century developed transfer principles for set theory. So this was before Abraham Robinson, but around the time of Hilbert and his interest in Cantor's set theory. Zermelo and Frankel worked on this stuff, and Montague especially worked on things called reflection principles. And a reflection principle is like a transfer principle, that a model of set theory can be expanded to another model of set theory, or reduced to a smaller model of set theory, where the things you are interested in inside the set, one of the set theories is true in the other one, as long as you're not referencing things that one of them can't see. That's roughly the kind of presentation I gave today anyway. Going back to Gödel, he solved another problem in a similar way, is to give us class set theory. And that way of doing it is in this same vein of having a reflection kind of principle and a conservative extension. So this is a conservative extension of set theory. Yep. And what he did was he said, well, there are some things that can't be sets. And so, for example, Bertrand's paradox gives us the class of all sets that are not members of themselves cannot be a set. And Gödel took that and ran with it, and he said, let there be some classes that are not sets. Okay. And then within the collection of classes, you have a model of set theory. You have set theory, actually. And so you've expanded your things to set theory. And as long as your formulas you're talking about don't reference the things that set theory can't see, then they are formulas that are true in set theory if and only if they're true in class set theory. Okay, that's roughly what it was. And the problem he solved by doing this is a very interesting other problem called the generalized continuum hypothesis. What do I mean by that? He didn't solve it completely in the sense that a lot of people wanted. It was already known by Sierpinski that the generalized continuum hypothesis implies the axiom of choice. But what Gödel showed was that every model of set theory contains within it another model of set theory, consisting of the class of all constructible sets. and that model always satisfies the generalized continuum hypothesis. So that means that if set theory is consistent, then the generalized continuum hypothesis is consistent with it. I saw a question pop up, a comment pop up, and that's a good comment.
Yeah, it was just, sorry.
Yeah, okay. Bertrand's paradox is the statement that there's a class of sets that cannot be a set. That's equivalent to Bertrand's paradox.
It's actually Russell's paradox.
Oh, yeah, Bertrand Russell. Yeah, thank you.
There is a thing in probability theory called Bertrand's paradox, but it's different.
I really apologize for that.
It's
a slip of the tongue, yes. I have no idea why I said just Bertrand. And so I wonder if we're getting close to time to stop, but I want to be careful about that. All right. So are there any other questions? Irfan, I hope that helped. Let me point out, in these early approaches to the study of set theory, a tool that was used by Gödel in particular is the notion of an ultraproduct. And Abraham Robinson used first the compactness principle of first-order predicate logic to prove that we can build a model of analysis where infinitesimals can be treated rigorously. But later, he and Zecon showed that you can use ultraproducts to construct such a model. Okay. And that's the method that is that's a method that's very strongly in use today instead of the compactness principle. There are other approaches to non-standard analysis that are more linguistic, like the original one by Robinson, and a notable one is by Edward Nelson, who was originally a probabilist and quantum mechanics guy. But he later wrote a book called Radically Elementary Probability Theory based on internal set theory, which he built around these ideas. Thank you.
Yeah, I think that's a very good point to stop our live YouTube broadcast part of the session. I think we'll still continue discussing these things offline. I thank Matt for giving us this talk and giving us this nice historical overview of how these topics emerged.